Hello and welcome to the long video for Exorcising Spectres with Secure Compilers. I am Marco Patrignani from CCS and Stanford, and this is joint work with Marco Guarnieri from India. In this paper, we provide a framework for studying security of countermeasures against Spectre v1 attacks. Then, we use the framework and prove that some countermeasures are secure, while others are not. Specifically, the framework is based off secure compilation results that phrase security of compilers as the robust preservation of properties and hyperproperties, and with robust, I mean in the presence of an arbitrary active attacker. In our framework, the property we end up preserving is speculative non-interference, or SNI, which is a semantic characterization of security with regard to Spectre attacks. Concretely, the source language of our compiler models is a standard imperative language. Unlike the source language, the target language is not standard and it has a speculative semantics, which is a kind of operational semantics that models speculation. And in this paper, since we focus on Spectre v1 countermeasure, the speculative semantics models branch predictors mis-speculation. Notice that throughout the talk, we'll use color blue for the source language and color red for the target one. With respect to the proofs, we apply our framework to several models of existing Spectre v1 compiler countermeasures and prove that ICC is secure, SLH is secure, but we'll see later precisely how, and then we devise SSLH, so a stronger variant of SLH. On the insecure spectrum, we use our framework to validate the fact that MSVC is insecure and that the interprocedural variant of SLH is also insecure. Now in this talk, I'll give you the details of the speculative semantics of the target language, define what SNI is, and then describe the formal details of the secure speculation framework we devise. Then I'll talk about the security results and about the insecurity ones. I'll conclude at the end with a technical remark as to how to do these secure compilation proofs. To explain speculative semantics, let's consider the canonical Spectre v1 snippet that accesses array B at an offset based on the value of array A at index x, where x is an externally supplied input that is checked to be within A's bounds. Let's assume that we run this program with A's size being 16 and the value at array A of 128 being 3. The center of the slide contains a depiction of the state machine modeling our language semantics. We start with the function being called, stepping to the evaluation of the body of the function with the actual parameter, the value at 128, replacing any occurrence of the formal parameter x. Now normally, this program would evaluate to skip, since the guard is false. However, during speculative semantics, we model the fact that a malicious attacker may have trained the branch predictor into mispredicting conditional branches, and thus we evaluate the wrong branch. And in this case, we go down the then branch even though we should have gone down the else one. We first access A of 128, producing an observable action that tells us we read that memory location, and then access B of 3, producing an observable action that tells us that we read that memory location as well, and then assign to Y. At some point, the speculation ends, and the state is rolled back, and it continues with the correct state being the skip. However, the semantics captures the cache footprint as traces, recording the fact that we accessed two memory locations under speculation. These traces model what an attacker can extract out of the state of the machine that has been not rolled back after speculative execution. Now, let's define speculative non-interference. SNI is a non-interference property, and as such, it requires reasoning about two runs of the program that start from low equivalent states, or rather from states with different secret but with the same public values. In this case, the content of A128 is secret, or H in non-interference lingo, and thus we can assume it to be different across runs. When the program runs a second time, it therefore generates another trace, which you can see depicted after the first one. Now, the second trace is different from the first one, which means the code is insecure. More formally, we indicate that a program is SNI as follows, with PEV-SNI, and say that a program is SNI if, assuming that its behavior when not speculating are equivalent, then the behaviors during speculation are also the same, equivalent. If this is the case, speculation does not introduce differences in the behavior. If this is not the case, then it is possible that speculation introduces security leaks, as in the case above. Now, the problem we face at this point is that proving SNI preservation through compilation is hard. And that is because SNI is a form of non-interference, which is a hyper-safety property. Now, preserving safety properties is much simpler than preserving hyper-safety ones. So we devise a safety property called speculative safety, or SS, and prove that SS over-approximates SNI. and resort to prove SS preservation then instead of proving SNI preservation. Now let's look at SS in more detail. The core mechanism at the center of SS is a taint tracking mechanism, which tracks taints associated to data, to the PC, and to the actions of the semantics. Taint labels are derived from the integrity lattice, which is the dual of the more standard no-interference lattice. We have label S, which means safe to be communicated to the attacker, and label U for unsafe, which is stuff that should not leak to the attacker. Here, we consider the same snippet of before, and we see that the PC starts with S, safe, since no speculation is ongoing. We then hit the conditional, and at this point, we start speculation, with the PC whose taint is raised to U. The first read is from a constant address, 128, and constants are safe, because they do not depend on secret data. The semantics thus generates an action tagged to the greatest lower bound of the taint of the PC and of the data, which is S. Then, the second read is performed, but here the data we are reading is not constant, and it comes from secret memory. Intuitively, secret memory is U, unsafe to leak to the attacker. So the action generated now is U, because that's the greatest lower bound of U, and the read is thus unsafe. Execution is rolled back as before, and we are left with one tainted trace, and we can define SS to be the absence of U actions in any program trace. In this case, because there is a U action, the program is insecure, as expected. As premised, we define SS as an over-approximation of SNI, and this is what we proved for the target language. In the source, on the other hand, there is no speculative execution, so even for SS, the PC is never raised to U. So effectively, SS and SNI coincide in the source. And this makes sense at an intuitive level. The source is where the programmers reason, and they do not reason about speculative execution. With SS defined, we can show our first criterion for secure compilation that states SS preservation. We call this criterion RSSP for robust SS preservation. The statement reads, if any program is SS for any source attacker it is linked against, then compiled P is SS for any target attacker it is linked against. While the statement is useful from a security perspective, it is less so from a proof one. So in the spirit of secure compilation, we devise a second statement, equivalent to the first, but more amenable to proofs. We call this RSSC for robust SS compilation. And it says, for any prefix M that compiled P does when interacting with any target attacker, there exists a source attacker A that makes P do the same prefix M. And in this case, the prefixes are not exactly the same, but the target one can at most extend the source one with S actions. If this is the case, it means that any target behavior M can effectively be replicated in the source, but the source has no speculative execution. So if this is the case, it must be that the compiler prevents any leaky speculative behavior. In these criteria, we see we have explicit universal quantification of the target attackers. This makes our attacker model stronger and more precise. The attackers we consider are precisely those that can be expressed according to the target semantics. Finally, we prove that RSSP and RSSC are equivalent. So we can use the first in order to understand the security implications of our proofs, and the second to do the proofs. With this, we can discuss our secure compilation framework against Spectre, which is depicted on the slide. In order to show that compiled code is SNI robustly, that is, against any attacker, we must show that it's SS robustly. And in order to show this, we must start from any source program that is SS robustly, which is any source program, and use a compiler that is RSSP. For simplicity of proofs, since RSSC compilers are also RSSP, we just have to prove RSSC and the whole chain of implication is satisfied. To be precise, in the paper we consider two variations of SS and SNI. A strong one, denoted with a plus, that prevents all speculative leaks, and a weak one, denoted with a minus, that prevents leaks of data accessed non-speculatively. These two variations yield two different target languages, since they rely on two different taint tracking mechanisms to be implemented in the semantics. The reason we define these variants is to be able to characterize the security of these two snippets. The top one is the classical Spectre snippet that we saw before. The second one is analogous, except that it loads from A outside of the branch, and thus before speculation. The first snippet violates both variants, but the second snippet only violates the strong variant, and it is deemed secure for the weak variant. Now, let's see the compiler and the statements in action. We take the ICC compiler that puts a speculation barrier, or L-fence, after any conditional, so we have the source program in blue and the target program in red. And the only difference is the addition of the L-fence in the target program. When program starts executing, we hit the branch, and then we speculate into the body, where we hit defense, which stops speculation altogether. Since no U actions are made, It is clear to see that this compiler preserves SS and it is therefore secure. Let's consider the SLH compiler now. SLH, as we can see in the compiled code in red, applies a mask to read values. We'll see the details of that mask in a second. So execution hits the branch, speculation starts, and we hit the mask, which is a conditional move of a constant 0 in place of the value to be read. The internal condition of the conditional move is the inverse of the branch condition. So in this case, we can see that the conditional move evaluates to true since the branch condition was mispredicted and evaluated to false, and the constant 0 is loaded instead of A of 128. Now, since 0 is a constant, its taint is S, and the constant read from B of 0 is also tainted S, despite it being executed speculatively, since it does not depend on secret, but it depends on the constant 0. To be precise, we prove that the original SLH preserves SS-, the weak variant, but it does not preserve the strong one. This highlights a benefit of our framework. We can perform a fine-grained security analysis based on the different secure compilation criteria we have. We have also defined a variation of SLH that preserves strong SS and strong SNI, and that can be found in the paper and in the tech report. We also have some unsurprising insecurity results. We could prove that MSVC and non-interprocedural SLH are both insecure, so they cannot be proven secure in our framework. And that is because essentially they lack some L-fences. Finally, let me conclude this talk with a little technical insight into the proofs. Here's the general scheme in which these secure compilation proofs for Spectre are organized. We have a source execution in blue and a target execution in red. And execution can be of three kinds. Either only the attacker executes, this is the top left and the top right areas, or only the program and its compiled counterpart execute, this is the top central area, or either the context or the program execute in the target according to speculative semantics. This is the bottom area. The point of the proof is preserving a relation between source and target states during execution. This is the dotted line that connects the states, where this relation ensures that related states make the same action. This part is not particularly complex. What is complex is maintaining this relation during speculation. Essentially, we have to be able to enforce a stronger invariant during any speculative execution, namely that any action M sigma done during speculation has a taint sigma that is S, therefore safe, and reinstate the relation with the source states after speculation ends. The stronger invariant proved during speculation ensures no violation of SS is introduced in compiled code. That ended my talk. I look forward to receiving your questions during the conference, or if you're watching this at any other time and still have questions, please drop us a mail.